Hello everybody, my name is Tefik. Today I'm going to present the last video of the stress-based casing design video series. So before I move into the Excel solution, I would like to do some recap of the first four videos that we have done so far. So on the part number one, what we have done is we have done the proof, or we proved the uniaxial burst, which is known as Barlow equation. So how we have done the proof is basically we used basically we have taken the von Mises yield criterion, and then we said that the radial and the axial stress is zero and external pressure is zero. Therefore, the tangential stress is equal to the yield strength, and basically we have solved for the internal pressure, and then also we have included the 87.5% API wall thickness tolerance. And then we have done an introduction into the von Mises yield criterion, and we have used that one to basically to do a thick wall proof of the burst uniaxial burst setting. How we have done that one? We basically this time we assume that there is a radial stress, and then we know that it yields in the inner wall. So we solved the inner wall for the radial stress, and then basically by assuming the axial stress being zero, we put this into the von Mises yield criterion, and then we came up with another internal pressure. And then this internal pressure was, if you remember, was very similar to the Barlow equation. There's a very small difference. So then we talk about the von Mises yield criterion, of course, and then we said that we will concentrate on a no rotation case. Basically, we are not rotating the casing where the torsional stress is induced, and then therefore we have three principal stresses, meaning radial, axial, and the tangential stresses. So on the part number two, we covered the API collapse regimes, and we started the video by proving the yield collapse, which is the lowest region of the API regimes in that diameter over outer diameter over thickness versus the yield strength plot. So how we came up with that one is basically we assumed that radial and axial stress being zero, and that the internal pressure being zero. So we solved the equation for external pressure, and then that equation is basically tangential stress is equal to yield strength, and then we solve the equation for the external pressure. And if you remember, for the other API collapse regimes like the elastic or the transition or the plastic regimes, they were kind of those numbers or those regions came up with based on some test, some physical specimen test. Therefore, there were some limits on the diameter over thickness ratio, how each region transitions to another region. On the part number three, we covered the axial tension or compression. So we basically started with main concepts being the true tension or the effective tension, and then as you remember, effective tension was excluding the effects of the hydrostatic pressure. And we looked at a case where the casing is cemented, and there's some initial conditions. You have the mud spacer and the cement weight on the outer area, and then you have the basically mud, and then you bump the plug, and then basically you bump the plug, and then you basically take it up to the casing pressure test value green cement, and then you take the pressure out. So what will be the initial tension profile of the cemented? So we calculated that it is basically the result of the difference between the outer area and the outside pressure, and then inner area and the inside pressure at the shoe, and then the effective tension at the shoe is zero. We have shown that one. And then what happens is during the life of the casing, the load cases and the in the life there is some effects basically induced by or there is delta tension or delta compression induced by different concepts. So we covered the ballooning forces, and then we proved that one, temperature effects and the drag force, and we also showed the proof of the bending and the shock loss. Maybe not the proof, but we have shown the concepts of the bending, which is mainly dependent on the dog legs, and then the shock load, and then I have mentioned to basically approach the shock loss as with precaution. However, the ballooning and the temperature effects was proved on that video, and the main thing that we have used was basically in the cemented interval the strain was 0. So the strain basically was basically stress over your Young's modulus, and then we have shown that basically 2 times the Poisson ratio to go from the axial strain to the radial and the tangential, and then basically this ballooning force we found that the net ballooning force is equal to 2 times the Poisson ratio, which is 0.3 for steel, and then you have the delta difference in the multiplication of the internal pressure times the inner area minus the delta of the external pressure times the outer area. So what we said is there's the initial conditions where it's cemented, and then there's the life of the casing, where basically all these effects are put into, and then you basically sum everything up to come up with a final tension profile. On the part number 4, what we have covered is we said, okay, now we have the concepts. Most of them are uniaxial, but we know that the three axes like the radial, axial, and the tangential stresses act at the same time. So how we gonna apply all of them, and then how we gonna produce a design limit plot with an ellipse, so that we can plot the uniaxial limits and the ellipse. So we first looked at the yield criterion, von Mises yield criterion, and then our purpose was to basically put this yield criterion into a simpler equation, so that this plus over here, so that we can basically solve for the delta P. So we basically with the torsion being 0, we easily transformed the yield criterion into the square of basically tangential minus radial stress square plus the axial minus radial stress square minus tangential minus the radial times the axial minus the radial. So as you see, the principal stress number 1 is being the difference between tangential and radial stress. The principal stress number 2 is the difference between axial and radial, and then basically this equation resembles to this general equation. So we could use Dr. Kuznicki's semi-major or minor method to put this in an ellipse format. So that was the first method to solve this one. The second method was basically to show the proof of each ellipse, and then to basically come up with the exact solution for the delta P, or the differential pressure, or the difference between internal and external pressure. How we have done that one? So we came up with this principal stress simplification of the principal stresses, and then we basically take the difference between the tangential and radial stress, which is simply 2 times the delta P times the outer area divided by the cross-sectional area. We take the difference between the axial and the radial stresses at the inner wall, and then this simply transforms into axial stress plus the internal pressure, because we know that the radial stresses at inner wall is basically minus internal pressure. This is regardless of the pressures in inner areas or outer area, or regardless of anything. So we came up with this simple equation, and we know that quadratic equation like this one, ax squared plus bx plus c, I could send the yield strength square to the other side to come up with 0 on this side, so that basically I could solve for x, and then we know that the root of x is equal to b plus minus the root square of b square plus minus 4ac divided by 2a. So over here my basically over here the what I will solve is for delta p. So we basically, if you remember, we expanded this equation, solve for delta p, and then we found delta p versus axial stress plus the internal pressure, right? And then this was the basically the collapse side, which is this part, okay? And then the backup pressure was the internal pressure. And then also on the second one, what we have done is basically we wrote the pi in the version of basically delta p plus the pe, because we, you know that delta p is p minus p external, or pu minus pu, right? So that's why we wrote this equation, and then we found the other equivalent, delta p versus axial stress plus the external pressure. That was the burst ellipse, which is the upper side, and so those two solutions gave us the exact solution, exact root for delta p, which means delta p on the lower side is the collapse rating, and then delta p on the upper side is the burst rating. So when we come to this design limit plot, to do a recap. So on the part number 1, we covered this part, uniaxial burst rating. We proved this one, and then we shown that design factor, you could see it can come down if you increase the design factor. Part number 2, we covered this part, and then if you remember, this part was a pure effect of tension on the rating of the collapse value. And we said that it is different from the temperature duration on the yield strength, because we know that temperature has an effect on the tension on the yield strength. So that yield strength, if there is a duration on the yield strength, this can affect both burst rating and the collapse rating later on. On the part number 3, we covered this part, uniaxial compression and uniaxial tension, which combines to this line. And then we talk about the different changes, and also we talk about, if you remember, there might be some performance difference between the casing and the connection, other than just the design factor, on some kind of low clearance pipe. You could have some, for example, 80%. You could have 80% of the tension or the compression rating of the body. You could have that in the connection. So connection might become the weaker part over here that needs to be shown on the design limit plot. And then on the part number 4, we came up with this triaxial ellipse. So we have shown, as I mentioned, two methods. One is the semi-major and then minor method, and then the second one is using the delta P versus stress plus the backup pressure. It's either an internal pressure for the collapse side or the external pressure for the burst side. So we shown two methods, and then we came up with this ellipse, so that we could see the overlapping region or regions that basically exceeds the uniaxial rating of the pipe. So I think we have done this one. We did a quick recap. Now I'm going to move into the Excel solution of the design limit. Okay, so for our test case in the Excel spreadsheet, we used the paper 185941 as the load cases, and then basically I developed this spreadsheet so that I can plot the uniaxial limits as well as the triaxial limits, and then compare those load cases with this design limit. So on the top part, as you see, it's a 958 L80 80,000 psi yield strength, 53.5 pounds per foot casing. And here you see the nominal wall thickness, and you see the internal, external, and the cross-sectional area. So the top part of this performance rating top is basically is the collapse region, API collapse region. So as you remember from our discussions, we know that the API collapse regimes refer to different regions with some constants from A to G. And then given the constants and given the diameter of thickness ratio and the yield strength, the casing can fall into different collapse regime. So for the 958 casing, it falls into the plastic collapse regime with this diameter of thickness ratio and the yield strength. So that the equation that we apply to the casing is the for this reference is the plastic regime, which is 6617, and I think the spec value is 6620 psi. So it's always a good check where the casing falls into the onto API region, which API region, so that you could have a visual, and also you could have a cross check of the value with the spec sheet. So I need to tell that I'm not applying any temperature duration. Temperature duration is kind of a vendor specified values for each temperature increments. So the next part that I'm gonna talk about is the collapse ellipse. So in the part number 4, we have derived an equation for delta P in the triaxial state for a given reference of tension plus the backup pressure, and then for collapse region, the backup pressure is the internal pressure. And also we mentioned that the uniaxial collapse regime for the uniaxial collapse in the design limit the design limit plot, in the positive tension the rating happens because of the positive tension, and also the API refers to that one. So that I made this table, which the values are taken from the different scenarios. As you could see, with different tension values from 150 to 1.22 million pounds. So as you see, at every different tension, there's a calculated yield strength, corrected yield strength. The yield strength doesn't reduce, but for the formula for the API collapse regime, it is recalculated, so that this new yield strength is fed into the new API collapse regime equations by calculating different constants, and then you come up with different uniaxial or API collapse pressures. And those collapse pressures I put in the table because we will use these values to populate the collapse derating in the design limit plot. So the top part, okay, we say collapse region, and then I basically put some arrows where the values are coming from. So and then I basically copied the derivation here. So how we have derived this, basically we put the von Mises yield criterion into this form, and then from this form onwards we basically inserted the principal stresses, and then we basically solve for delta P using the quadratic quadratic equation solution. That's basically, you can see in this format. So with the reference of tension and the backup pressure, or for this case in internal pressure, we have calculated some delta P or collapse pressures at this reference points. We could also specify the tension and the backup pressure into PSI, or we could do that into pounds using that cross-sectional area conversion. That's why I have these two tabs that are in PSI, x-axis in PSI, or x-axis in pounds. Of course, the x-axis in PSI is easily comparable to a yield strength of the pipe because it's PSI to PSI comparison. On the bottom part, I have the burst ellipse, which is the backup pressure is external pressure, and in this paper, the derivation was originating from the circle of plasticity, and if you remember, circle of plasticity was basically using the effective tension. All right. However, I derived this equation. I put the whiteboard here as well. I'm gonna upload these pictures as well so that maybe it's easier to follow some derivations from picture for some of you. And then as you could see, I used the same von Mises yield criterion and then using the same principal stresses. However, this time I rewrote P internal pressure into external pressure plus the delta P, and then that's why I was able to pull the delta P to an equivalent or to a function of axial stress plus the backup pressure, and then that's the external pressure in this case for burst, and then I basically renamed some ratios into different letters. So I called it A. That's why I called it A here, so that you can follow easier. And then 1 minus outer area divided by cross section is also another value. So same as the collapse ellipse. For the burst ellipse, I have a reference. I have a predefined tension values that I just basically randomly picked up with the same increments, and then basically I calculated the delta P, which is the burst rating in the triaxial state. On the next one, I basically put the Uniaxial design limits. To be able to populate the Uniaxial limits on our design limit plot, right? So I have the Uniaxial burst limit, so I use the Barlow equation here for including 87.5%. If you use the Barlow equation but not the API thickness, it goes up to 9060 psi, which I'm gonna show you why how this pressure lies with the ellipse equation. And then I assuming that 100% connection performance, meaning that connection is as strong as the tension and compression. Usually they will have the same burst and the collapse rating. However, sometimes with special clearance pipe, the connections might be lower. But for this case, I assume the body is as strong as the connection in terms of tension and compression. And here I basically assumed all the design factors of 1, and then just for your interest here, so if we for example calculate the API tolerance, my cross section area come down to 13.7 inch square from 15.5, and also that resulting stresses will be higher. So I put some different scenarios here in different columns. So in the first column, I have a wall thickness of API tolerance, including 7.5 and the 1.25 design factor, so that your yield strength is 64. That's basically 80 divided by this one. However, I used this column to plot it compared to my Triaxial, because I used 100% wall thickness, which is basically nominal, and then the 100% one design factor of Triaxial in my burst and collapse ellipse. That's why I'm gonna use the method of semi-major and minor, using the 100% nominal wall thickness and the one of design factor. So if you remember Dr. Kutnitsky's video, I put that the video link under the part number 5 in part number 4 in YouTube. So with a given yield strength of the pipe, of course, with a given area, outer area and the cross-sectional area, you develop an ellipse with a x-axis and a y-axis, right? Corresponding x and y values. Basically, you transform that one so that I presented this as one method of building this triaxial ellipse. So there were two methods. One method is, of course, the derivation of the delta p, finding the delta p in terms of principal stresses, or deriving the principal stresses to come up with the delta p value in terms of tension and the backup pressure, which is internal pressure for collapse and the external pressure for burst. So this was the one method. So you have a delta P versus tension, or let's say x plus x versus y. Okay, and then again same as x versus y. That's why I put delta P is y axis. Or that was the first method. Or the second method was this Dr. Kurtich's what I just call for simplicity semi major and minor method, which I basically you were gonna find the semi major and semi minor, and then you basically transform into the ellipse. So before we are able to use this ellipse, we would like to check if this ellipse is right or wrong. So that's what I have done in this step. Basically, I plotted the first two columns, and then after I plotted the other columns after the angular transformation. So you could see that the ellipse is crossing 80,000 psi, which is the yield strength at every axis, and you could see that the design factor is 1, and then design factor is 1. If you increase the design factor, what's going to happen is the ellipse will become smaller. For example, a triaxial design factor 1.25, you are ending up with 64,000 psi. So this axis will cross from basically 64. Let's do that quickly here. For example, if I put 64,000 psi here, for example, okay. So what's gonna happen is you could see that ellipse was now or was crossing from 80k. Now it's crossing from 64k. So I return back to the original value. All right, and then I move to my load cases. So for the load cases, to be able to test our design limit in Excel, I have basically used the SP paper of 185941 as reference. So I used their load cases. So they had the load case of bracket shoe minus full gas to surface, and then they had a collapse load case of loss returns. So I used these load cases. So I copied all basically the information over here. Okay, all the slurry densities, when the mud weight was, what the mud weight was when casing running hole, and then all the geometry, and then all the gas gravity, and the molecular weight, and then the temperature information, and of course of course the tension profile is calculated here. So how I calculate, now I'm gonna show that one. So in the part number 4, what we said is basically in the part number 4 we set the final part number 3 we set the final tension profile of the casing is basically is calculated from the initial condition states up to the final state by taking into consideration of the ballooning, temperature effects, drag, any bending, and the shock loss. So I think this well is a vertical well, so we don't need to worry about the bending. So there's no dogleg here, and then it's no side force. So we let's ignore the drag force. Let's ignore the shock load as well. For installation cases, now we have of course the kind of live load case we are drilling the next hole section, and then 958 casing is exposed to this the load case of basically the frac. So the shoe is fracking, and then you have a full gas to surface, to calculate the internal pressure profile, and with a given external pressure profile, you calculate your delta P, and also with all the forces from the initial conditions, you come up with a tension profile, and then from that you come up with your triaxial design factor, or you will basically use this tension versus the delta P profile, and then compare with the design limit uh, for the triaxial and the uniaxial limits. So what I have done here is basically I calculate upside down. I put the depths upside down. You need to remember that all the time we need to work with the TVDs. Okay, it's from hydrostatic basic assumption. And then for this internal pressure, how I calculated the internal pressure is basically, if you look at the Ted Brome's book for the casing and liners for drilling and completion, you will basically see the formula of basically with a given temperature profile, with a given molecular weight, you are basically able to calculate the internal pressure from a given reference point. So we know that there's frac at the shoe, so the shoe is at 15,000 feet, and then we know that the frac pressure at that shoe, uh, that's your original pressure, and then from that point onwards, because gas is compressible, your temperature and the pressure is gonna your temperature is gonna and the pressure is gonna affect basically how it behaves. So you could see how the internal pressure is calculated. So I marked this one as the top of cement, because we know that for ballooning force, strain is zero in the cemented interval. So we know we come up with an exact ballooning force in the cemented interval. Okay, so as we mentioned, different companies have different external pressure profile. In this load case, specific load case, the external pressure for this load case was given by the mud weight running hole. So if you see the calculation here, that was mud weight running hole, and then in the cemented interval, it was the cemented mixed water. So you could basically easily calculate the hydrostatic pressure profile on the outside of the casing. So the internal pressure profile, as we mentioned, is basically calculating based on the compressibility. So you calculate the internal pressure profile that was originating from the fracture pressure at shoe, with a given temperature profile, with a given molecular weight, or the molecular weight, and of course it's kind of the gravity, which is the molecular weight of the gas with respect to the reference to air. All right, so you could easily calculate the delta P, right, from internal to external at every TVD, and I put some remarks here. That's the shoe, that's top of cement, and that's at the surface. And for the initial conditions, as we mentioned, this is our reference point. So the initial conditions internal pressure is basically, as you know, that is the mud weight that we are running in hole, right? But the external pressure for the initial conditions is the cemented slurry with the basically in the green state. So you calculate the external pressure profile based on the slurry densities, spacer, and the mud weight on the annulus. So the equation that we used to calculate the true tension at the shoe and true tension at the surface, is you see the profile from bottom to top. So now what we need to calculate is the ballooning. So the ballooning, we know that the ballooning, the strain is zero at the cemented interval. However, above the cemented interval is kind of not an exact or accurate value. Overall, I think the tension, because you have such a large design factor in tension or compression of 1.4, you are kind of taking the uncertainties into consideration. However, for the cemented interval, I think we have an exact value. However, above the cemented value, it's kind of an estimated value. So we could say maybe a better assumption is to take a midpoint above the top of cement. So we have a ballooning force which is basically 2 times the Poisson ratio, and then you take the change in the internal pressure profile and the change in the external pressure profile from initial conditions. So as you could see, let's click on one, and then let's see which numbers is taking. So you could see the internal and external pressure of the load case and the initial conditions, which was our reference state. So we take all the ballooning forces in the cemented interval using the Poisson's ratio, and then we take a midpoint approach above the top of cement. So let's come to the thermal stresses. So what I have done is here on the right hand side, I basically take the undisturbed profile, which was given in the load case, and then the temperature profile of the load case was given as well. Okay, so I basically calculated the thermal stresses by using this formula, which was given when I was going through part number 3. And as you see, there's some from disturbed to the load case. There's some cooling here. Okay, that basically induces some tension, and then most of the part is all cooling, and then you have a huge tension that is caused by the thermal effects. Right. So what we need to do is we have as we mentioned, we have initial conditions. We have a ballooning, and then we have a thermal stresses. So we take the bending as 0, and then basically we come up with a final tension profile, which is basically initial tension profile. As you see, initial tension profile plus the ballooning plus the thermal and plus the bending, and this is in the cemented interval, and above the cemented interval is where I basically take the mid approach for the ballooning, and then I basically do the same approach for thermal stresses, and basically you come up with kind of a final true tension profile. So now we have a delta P, and we have a true tension profile. So at the bottom part, what I do is basically, okay, I take the same values from below and above, and then I will calculate the principal stresses on this column. So you have each TVD, and then you have basically the final profile, which is basically taking the number from your final true tension profile. Okay, and then you basically calculate into PSI. You can convert it by the cross sectional area. You have the delta P difference, so you can calculate the three principal stresses. So you have the tangential, you have the radial, and then axial. We already have the number from the final true tension profile. Into of course we converted into stresses, and then you need to calculate both in the inner wall and the outer wall by setting r equal to inner radius at the inner wall, and then r equal to outer radius at the outer wall, and you will basically take the highest number to be able to calculate basically lowest design factor, triaxial design factor, which is calculated here. So I basically divided them into their into the yield strength basically. So you take the conservative approach there. And then as I mentioned, I didn't do temperature duration on the yield strength on this example. All right, and then I basically used the nominal wall thickness. So here I put these two columns here to be able to plot them onto our triaxial ellipse solution for the burst ellipse and the collapse ellipse. So I have the x as the tension, which was basically conversion of the true tension plus, because plus the backup. This is the burst load case. So burst load case, which is basically you have the external pressure as the backup, and then you can of course plot this in pounds, as well as you can plot this in psi by using the cross sectional area and then convert it. And then y is your delta p, and then because it's a burst load, it results into a positive differential. However, as we mentioned, the different companies run on basic different external pressure profiles, so it doesn't mean that the differentials are will be big in quantity. They might be small, but they might be different as well. So external pressure profile is important again to mention here. So again, to recap, we have taken a frac HU minus full gas to surface load case from this SPE paper. We referenced that one, and then we used the assumption of this load case, including all the fracture gradient, slurry densities, mud weights, and the external pressure profile and the temperature profile. So we calculated the initial conditions tension profile. We calculated the resulting ballooning because due to a different pressure profile of load case, bracket shoe, minus the full gas load case, and then we calculated the differential pressures and the tension profile. So in this tab is basically I plotted how the undisturbed profile, and then how is the burst load temperature profile that was given in the load case. So as you can see, there's a bit of a cooling here, which results into a high tension. So that the tension is superimposed onto the initial conditions. So now this step is about the collapse load case, which is the loss returns. So basically what happens is, the fluid level drops into casing when you are drilling the next hole section. So the external pressure profile is basically on this one is mud weight running hole, as you see here, and then the internal pressure profile is you have the fluid density of 8.33 below the 2000 feet mark. So up to the shoe, you still build a kind of pressure profiles. So that's basically 2000 feet up to 15,000 feet. So there's a 13,000 feet of column here that's calculated, and then as you can see, above 2000 feet there is no there's no pressure because it's you lost the returns, and then the fluid level is at 2000 feet. So the external pressure is again easy to calculate, the mud weight running hole, and then your delta P is calculated, and again you go back to your initial conditions. Initial conditions is same as it was given in the burst the other tab, because this casing was cemented, and then that casing is cemented in one condition, so that basically gives you the initial condition. So the true tension profile is same, isn't gonna change. What is gonna change from the burst load case is the ballooning and the thermal profile. I think the temperature profile is same for the burst load and the collapse load case, which might not be very realistic, but just for the sake of load case, the thermal stress is the same. So I took from the other column, from other tab, the calculated values. What is different is the ballooning. Of course, now what happens is you have the internal pressure is lower now, because on the first one you had of course the gas kick originating from the frag pressure at shoe, the full gas to surface, sorry, so that you have a higher internal pressure. This time you have a lower internal pressure, and external pressure is higher, However, in the burst load case, if you remember the external pressure load case, if I'm not mistaken, it was kind of a mud weight running hole above the top of cement. However, below the top of cement, it was cement mixed water. In this case, it's full mud weight running hole, so it has a higher external pressure profile. It's the nature of a collapsed load case because you want to maximize the differential and then to see if the casing will withstand, right? So the ballooning is calculated in the same way. Let's click one and then see how it's calculated. So it's still the 2 times Poisson ratio. You take the final you take the differential of the difference in the internal pressure and the difference in the external pressures multiplied by the area. So you basically calculate the ballooning and thermal on top of the initial conditions, and then you come up with a final true tension profile. So I put this one from our whiteboard. So as you see, the final load case or true tension profile is basically true tension profile of the initial conditions plus ballooning and temperature. Of course, if I had the kind of a bending or the drag happens, that will be considered in this initial conditions, because if you have a drag, you are running in hole, you will have lost that weight for the to the side load or the side force or the drag force, and then you will have induced some bending stresses with a given dog legs in the well. However, as I mentioned, this is a vertical case, so to keep it simple, we don't worry about those things. Yeah. So and then on the bottom part, same as I have done in the burst load tab, I have basically calculated the principal stresses. So axial is calculated from outside, and again this is a case where the nominal wall thickness is used, so this 100% wall thickness, and then you calculate the tangential and the radial stresses basically on the both in the inner and the outer, so that you basically take a conservative assumption of taking the highest von Mises stresses, equivalent stress. It's either on the inner wall or the external wall. As you could see, the highest is the inner wall. So it supports our assumption of it yields at the inner wall first, and then you calculate your triaxial design factor accordingly. So for building our design limit plot with the load cases, you still have the x and y axes as I drawn here. So one is in pounds. Because it's a collapsed load case, the backup pressure is the internal pressure. So if you look at this one, it will take the internal pressure over here, and then you use the cross sectional area to come up with the pounds, and then you can do that in psi as well. So let's go into this plot. So let me a bit maximize this one. So there's lots of colorful lines here you can see. So I will use this one. So first of all, that's your collapse ellipse. That collapse ellipse is the values is taken from the performance rating, which is basically this part. Okay, and then the collapse values or limit is taken from this top part as in the triaxial state. So that's the collapse part, and then there's the burst part. So that burst ellipse is taking the values from here. So basically it's simply plotting the x versus y, which is y is the delta p differential pressure, internal minus external pressure, and then your x-axis is tension, or you can define it into psi terms. But of course, in both cases, you need to account for your backup pressure, which is your internal pressure for the collapse, and then external pressure for the burst. So then we have what we have is the semi-major and minor solution. So this ellipse with specified this yellow ellipse that you can see with the yellow squares is basically taking values from the Dr. Kuczynski's method of the semi-major and minor. Basically, with the yield strength of the pipe, I take some one design factor with a 100% nominal thickness. I come up with kind of a transformation of the ellipse, as you see, and then you can come up with a ellipse that crosses all the yield strength at 80,000 psi. All right. So what we need to talk about something else here is the uniaxial limit, of course. So uniaxial limit, so you see here, this is the 100% wall thickness, right? So why I plotted that one is because to show to the comparison with our burst ellipse. So the burst ellipse and the 100% of the wall thickness uniaxial limit crosses at very similar points. So this is one thing to note. However, when we talk about the 87.5% API tolerance, it basically comes down to 7927 psi from 9060 psi almost, right? And then we have the uniaxial tension and the compression limits. So that's the compression limit, and that's your tension limit. So because our x-axis in psi is easy to plot this. This is 80,000 psi. You don't have to worry about the cross-section area here. Okay, and then your uniaxial collapse, as you see, is the plastic, because our number falls into the plastic collapse region. Our casing falls into the collapse region is 6617 psi. However, as you see, you have the duration of the collapse rating with the positive tension. So that white area is basically taking values from this small table. So that's you are derating your collapse, uniaxial collapse or API collapse based on the tension. Okay, so as mentioned, this is different from your duration of the yield strength based on the temperature. So that's different. And then I have plotted here another circle. So this is 1.25 design factor and 87.5% wall thickness. So you could see this was taking the values from this semi-major minor method using this one. All right. So now yield strength is based on 64,000 psi plus you take this 87.5% wall thickness, meaning that you have more stresses because your cross sectional area is smaller, so you have more stresses. That's why your ellipse is much smaller here. So this ellipse was basically 100% wall thickness and one design factor, as you can see on the legend on the plot. All right. So now what we have left is we have the first question before we move there is why you could ask the question why the semi-major and the minor method and the collapse triaxial collapse is exact same solution, as you can see. So it is basically this one, and then your collapse ellipse is this one. So it's basically both is exactly same. Okay. But then you could ask the question why the burst ellipse and the semi-major and minor method doesn't yield into the exact ellipse on the burst side. Well, the answer is I thought about the answer, but I think the answer is this one. So when you are building your semi-major minor method, you are taking this one into account, meaning that your principal stresses are this one and 2 is this one. However, so your delta P is basically your principal stresses divided by 2 times outer area divided by cross sectional area. So this is an exact solution for the collapse region, right? However, in the burst region, the equation is getting more complicated. So what you need to do is, for the burst section, you need to come up with a solution where you have exactly this one, principal stress to the square, plus the principal stress 2 to the square, minus principal stress 1 times 2. If you come up with a solution for the burst region, then your both ellipses will overlap. However, at this time, because our semi-major and minor method is originating from the collapse ellipse, because that's in basically principal stress 1 to the square plus principal stress 2 to the square minus the multiplication of principal stress 1 and 2. It is exactly the same solution as the collapse ellipse solution. This one I basically touch based on the recap video. So if you scroll back a little bit to the beginning, you will see what I mean. But what we say here is these ellipses of the burst and the collapse, they are exact solutions. They were I derived them from basically principal stresses. So they are exact solutions. So what I'm gonna do now is basically to point out at the load cases. So these load cases, as you see, the cases. So this one is the bracket shoe. As you see, it basically it's plotted on the burst side of the design limit. So that's the upper part. It results in a positive pressure. Okay, and then it has a corresponding tension profile. And here, this one is the collapse load case, and as you can see, it is plotted on the collapse. Excuse me, in the collapse region of the design limits, and it has the corresponding delta P values. So I put them into the 10 to the 5 or 10 to the 4 format here. So you could see the highest pressure over here is in the stress format is 47,000 psi. However, it comes down to almost 17,000 psi. Into of course, this is the axial stress plus the backup pressure. For collapse is the basically the burst pressure, and sorry, internal pressure. And as you remember, above 2,000 feet, it is zero internal pressure because of the loss returns. So you come up with kind of, and then this straight line is referring to your top of cement, where basically we followed an approach of a midpoint. So because you know that the strain is zero in the cemented interval, we have an exact solution with the Poisson ratio. However, above the cemented interval, the solution is not that certain. That's why we just basically took a midpoint approach both on the thermal stresses and the ballooning related stresses. So that's why you have this spike over here. But what we basically doing is here, what we basically do here is we basically plot this plot where is it plot basically x versus y is in psi from the corresponding load cases. So what we can do is I basically plotted the same one into the pounds as x-axis. So it's basically the tension plus the backup. So you could see the collapse load case and then the burst load case. So they don't change their corresponding region here. So your delta P is still delta P. What is changing is the y-axis is still same, delta P. What is changing is the x-axis. So you can see, I think it's one. I think the yield strength limit is 1.24. So as you see, those are 1.24 here. I use the design factor of 1, so design factor of 1 here, design factor of 1, and then you have a corresponding tension profile plus the backup. So that is plotted from this region and corresponding this region. So another observation here. So as we said, these are exact ellipses. you will notice when you plot this, you will notice that this ellipse solution, because there's a square root in the solution for delta p. After some point, it is hard to get a value, because that square root, if because there's a 0.75 multiplier over there. I think when the ratio of stress, when the ratio of tension plus the backup divided by the yield strength is above 115, you will get a negative value, or you will not be able to solve the root square of that one. Therefore, I think you will use kind of an approximation over here, because you know that at 1.24 it will be 0 here, and then 1.24 it will be 0 here. So they will combine kind of a here, so you can come up with a how do you say, you can combine the lines here. So again, same as the other plot, you have the uniaxial limit, burst limit. So here I used 87.5%. So include, that's considering the API tolerance. If I would use the 100%, it would have come to 9060, almost come to the same point where it crosses where the triaxial ellipse crosses the y-axis. Okay, and then you have the compression and the tension limit, and then, as I mentioned, all the design factors are set at 1 at the moment. So you can see design factor 100%. So if you take into 87.5%, what's gonna happen is your cross-sectional area goes smaller, your stresses is gonna go higher, and then of course if you increase your design factor, further the ellipse will basically shrink because of the wall thickness. And then if you increase your design factor to 1.25, which is kind of a general that I have seen, the ellipse is gonna shrink further. So another couple of assumptions or considerations that we can see, sometimes companies might allow a load case that is defined here, because they can allow some load cases that basically exceed the uniaxial burst, however still falls into the traction line, because of the improvement in burst due to tension. So some companies might allow that, but maybe not in the case. But again, the company standard is the main reference to work with. Again, this Excel spreadsheet, as I mentioned in the original LinkedIn post, is a test to basically put all the uniaxial limits and the triaxial limits, and then serves as a quick check for the load case. It does not replace any official procedure, which is probably done by an industry recognized softwares. But again, this is a quick check of the load cases, and also it's a good double check of how the design limits plot look like for a given yield strength pipe with the given geometry, nominal wall thickness, or the outer or the diameter, outer and inner diameter, and the collapse regimes, and plus how the ellipse behaves in the tension, with a given tension, and then how basically the ellipse behaves with different wall thicknesses, different, if you consider the 87.5% wall thickness, or with the different design factors. And same as for example, if I say burst is 1 here, and then if I take 1.25, I should, for example, you see the burst rating goes down, so that you have a higher burst, you have a higher burst design factor here. What did I use? 1.25. That's probably 1.1 is more realistic. So yeah. So it's a quick tool, but what we have shown here is I have shown I went through the each definition of the uniaxial burst, uniaxial collapse, tension and the compression limit on the lines, and then the rating of the collapse over here, as you can see, with the impact of tension. And then also I have shown the proof, or I have proved the burst side of the ellipse and the collapse side of the ellipse. In addition to plotting this ellipse with a semi-major or minor method. So this serves as a good check or a quick check how the load cases will look like compared to our design limit. And also we have shown, I think we have shown that basically the tension profile, the final tension profile, is basically a number that is superimposed on the initial conditions. And then major being the ballooning, major being the thermal, and then of course if you have bending or if you have drag force, they will be all considered. Okay, so you could basically follow the same procedure and then build your own work, how do you say, work procedure to come up with something similar. And I think you can build the same thing on Python maybe, or other sources, and you can maybe make the spreadsheet or a more user friendly version. So thank you for watching, and then hope this is a beneficial video for all of us. Thank you.